Hello everyone, welcome to another video tutorial of the course. In this video, we will continue settings of the dynamic simulation. So in the previous meetings, we prepared the model and we did a number of settings. So now I am going to set load parameters to be able to run the dynamic simulation. So here you can see the rotor of our case study motor, and this is the stator core, stator lamination, and the winding. So here you can see the model, and we defined the end connection, phase A, phase B, and we defined the analysis setup. So now I should define the motion band. So I select the motion band. As you know, motion band includes all of rotating parts. So from here, right click, assign band, and you know that the motion type is rotation. So in the mechanical tab, I am going to consider mechanical transient, right? We are going to simulate the startup of the motor, actually from the 0 speed to the steady state speed. So the initial angular velocity is equal to 0 RPM, the moment of inertia. I have one video on my channel. You can see the link here that is about calculation of the moment of inertia of the rotor of induction motor. So in that video, I explained how you can create the three-dimensional CAD model and how you can set materials and calculate the rotor moment of inertia. So I don't repeat it again. So I prepared this model before. You can see the rotor here. So I created the CAD model, as actually this is the rotor core and rotor cage. Also we have a shaft here, right? So I modeled these geometrical parts in the SolidWorks software, and I calculated the rotor moment of inertia. So here from evaluate mass properties, I can click on the shaft, rotor core, and finally rotor cage. So you can see the value of, you can see the IX, IZ, and IY. Actually, we need to know the value of moment of inertia around IX, that is 54509, right? The unit here is grams times square millimeters. But we need to, I copy this number, and here I paste. Here we need to set the value of moment of inertia in kg times meter square. So I should multiply this by 1e minus 9. Okay. So the next parameter is damping. What is the value of damping coefficient and how we can calculate that? I prepared this Excel file before, and you can see here we have some inputs and some outputs here. So now I am going to explain to you how we can calculate the friction coefficient. Okay. So this data, I got this data from experiment. you can see the terminal voltage here and the value of terminal current. So this is the RMS value of the terminal current and RMS value of the terminal voltage. And here is the input power, the RMS value of input current and RMS value of the input voltage, supply voltage. Also, I measured the current of each phase individually. This is the current of the main winding. Here is our connection. This is the main winding. Phase A is the main winding and phase B is the auxiliary winding. I measured the value of current in the phase A and in the phase B, actually main and auxiliary windings. So here I put the data, the main current, auxiliary winding current, right? 248 milliamperes and 124 milliamperes. So because we know the value of phase resistance and the phase resistance is equal for two phases, so we can calculate the copper loss due to main winding and copper loss due to auxiliary winding. So we can calculate total copper loss due to the stator winding, right? Also, we know the value of input power, and we know that the input power minus the stator winding copper loss is equal iron losses, rotational losses, output power, and rotor cage, right? So, in induction motors, we have copper losses in stator winding, and we have ohmic losses in rotor cage. We have iron losses in stator core and in rotor core. Also, we have losses due to friction and windage, mechanical losses, and finally, output mechanical power. So this difference is equal to this summation. So I measured the input power that is equal to 66 watts, right? And I measured the value of main winding current and auxiliary winding current, so I can calculate total copper losses. So input power minus stator winding copper losses is equal iron losses, rotational losses, output power, and cage losses. That is equal 28. As you can see here, we have a high amount of copper losses, and because this is a low efficiency, low power motor, the efficiency of this motor is low. Actually, if we calculate the efficiency considering iron losses, rotational losses, and cage losses equal to 0, the efficiency is around 43, right? Just I consider it stator winding copper losses. So it means the efficiency should be lower than or equal 43%. So if we assume a number for rotor cage losses and rotational mechanical losses, we can calculate the value of output power, and finally we can calculate the load coefficients. So we should assume these numbers here: output power, rotational power, and RPM. Actually, I should consider proper numbers here, and I should run the dynamic simulation. So for what value of output power I can reach the rated speed? Here, the value of rated speed is 2500 RPMs. So I should set this value such that I get this value of current. So because this difference is 28, if we assume 10 watts for iron losses and rotor cage losses and rotational losses, so we can say that our output power is equal 18 watt. This is an example because I want to run the simulation and calculate the steady state speed. So here, if I assume this value for output power and consider 5 watts for rotational loss, I can say that the output torque will be equal. This is the rated motor speed, 2400 RPMs. I can calculate RPS, that is RPM divided by 60. Also, I can calculate rated angular speed, right? Rated angular speed, 2 times pi times RPS. And I can say that the rated output torque is the output power divided by omega m, right? We have this equation, power is equal torque times omega. So I can calculate the steady state torque. And what is the friction coefficient? You know that the frictional torque is equal friction coefficient times omega. So if I multiply both sides with omega, this is the power loss due to friction, actually our rotational loss, and this is equal friction coefficient times omega squared. Finally, I can calculate friction coefficient using this equation. Total rotational loss divided by omega 2. That I implemented this equation here, right? Total rotational loss divided by omega m squared. By assuming this number, right? So as you can see, if we assume these numbers, the efficiency of the motor is lower than 30%. So we can try these numbers. So let me write 7.92 e minus 5, 7.92 e minus 5 is the friction coefficient. And what is the load torque? The load equation, we can set it like this. So here is the load equation, torque speed equation of the load. For fan, we can write the load torque is equal a constant A times omega squared, right? So the operating point, as you know, in induction motor, the operating point is intersection of the torque speed curve of the induction motor and the torque speed curve of the load, right? So this is A omega 2, and this is the steady state operating point. So we know this speed, that is 2400 RPMs. And we know this the value of this torque, right? The value of this torque, we calculated it here, 7.16 e minus 2. So I can write T is equal A omega 2. This is a steady state speed, and this is the steady state torque. Finally, I can calculate the value of A here, right? The load constant that I implemented this equation, the rated torque divided by the rated speed squared. That is equal 1.13 e minus 6. So I can write here 1.13 e minus 6. Right. So, we should implement a parametric equation here. Actually, the speed is an intrinsic parameter here in the ANSYS Maxwell software. So I multiply this by speed squared. The unit of the speed here is radian per second. And you know that for fan load, the direction of the torque, the load torque, is in the negative direction of the rotor speed, right? Actually, when the rotor speed is positive, the load torque is in negative direction. And when the speed is negative, the load torque is in positive direction. So I can use this function times sine of speed to detect the speed sign. And finally, I consider a minus here, right? Actually, to set the direction of the load torque, that is in the negative direction of the speed. So I did these settings. Now I can press OK. And we defined the motion band. We defined the boundary condition, end connection, phase A, phase B. We imported the external circuit, right? We created the external circuit. Actually, let me check again. This is our external circuit. Export it in desktop. Yes. And let's import it again. This is the external circuit. Okay. So now let's set the model settings. Actually, in the ANSYS Maxwell software, when we do two-dimensional simulations, the depth of the problem is 1 meter. So we should set the stack lengths, right? From Maxwell 2D, design settings, model settings, I should set the model depths. What was the value of the stack lengths? The stack length is 16, right? The stack length of the stator core and rotor core is equal to 16 millimeters. And the next thing that we should consider is the skew model, right? Here, as you can see, the rotor is skewed, and we should set the skew angle. Actually, we have a continuous skew for the rotor core. Here is, I know the skew angle, and we should set the skew for this simulation. So I check this, use skew model. The skew angle is equal here. Let me check. I know the skew angle. I measured it before, 16.36, right? 16.36 degrees. And this is number of slices for finite element simulation. Let's leave it equal to 5 and press OK. So design settings, model setting, everything is OK, and I press OK. So let's validate the settings. And we defined the boundary conditions, excitations, end connection, and windings. So Let's run the simulation and plot the value of the rotor speed, moving one dot speed, and calculate the steady state rotor speed. So let's run the simulation, analyze. The simulation is running. And here you can see the rotor speed, right? Okay, simulation completed, and now you can see the results. This is the steady state speed here, right? So why we got a negative speed here? Because of this circuit connection that I explained before. Actually, if we place the capacitance here, we can get a counterclockwise rotation, and if we place it here, we get a clockwise rotation. Pretty depends on the magnetic axis of the phase A and phase B. So for a positive speed, you can change the position of the capacitor. So let's interpret the results from here. Trace characteristics, all, average. I'm going to calculate the average speed. So I write here 1.5 minus 1.5 second minus 20 millisecond. That is one electric period, right? Add, as you can see, the average speed that we calculated is around 2000 RPMs. That is different from this value that I got from experiment. So let's plot the value of the load torque and the electric torque. So calculate the average values for the last electric period. 1.5 second minus 20 milliseconds. Add, the torque is 51 and the average electric torque is 68, right? The electric torque is consumed for the load torque and friction torque, right? So here we have 71, but here we have 68, and we have this speed. So also let's plot the branch current, terminal current, and calculate the RMS value of terminal current for the last electric period. From here, I plot the RMS value 1.5 second minus 20 milliseconds. Add is 373. That is higher than this one, right? Higher than this one. So it means our assumptions are not correct. So we should change these assumptions to get the right answer, right? So also here you can plot the rotor cage loss, solid loss. This is the rotor cage loss, and calculate the average value for the last electric period, 20 milliseconds, add, that is equal to 10 watts, right? So we got good results for the first iteration, and for the next iteration we should modify these numbers to get the right speed and right values here. So first of all, I cut this capacitor from here and I place it here, right? Because I want to get the positive speed. Maxwell circuit, export netlist, my circuit, yes, dynamic simulation, external, import. So we modified the circuit, and also we should modify the load parameters to get the right answer and the right speed. That is the topic of our next video. Thanks for watching.